those, and for my second lab, I'll be talking about motion of a falling object. First of all, we need to revisit Newton's second law and how it pertains to falling. Newton's second law states that net force equals mass times acceleration. In this case, we're only looking for position versus time in the y direction, and when you drop a ball, there are only two main forces acting on it, which are gravity and drag. The acceleration due to gravity is 9.8 meters per second squared, so the net force in the y direction would be mass times 9.8 in newtons in the negative direction, plus the force of drag, which would be a smaller positive force until the object reaches terminal velocity. In other words, F net equals force of gravity plus the force of drag. So here's our tracker. As you can see, I'm dropping a tennis ball from about a meter high, and as you can see, the graph follows a curved pattern here as the velocity seems to be increasing as time goes on. Our next task was to create a model of this. Our first model does not include drag and assumes that the only force acting on the ball is in fact gravity. So when you run this program, you can see the ball falling, and as you can see, the position versus time graph is still curved like the last one, but as you can see here, velocity versus time is a completely constant value, and it was clearly seen in the tracker data that that velocity was not constant. It also further, when you see the graphs side by side, you can see that the predicted position is clearly underestimating the actual experimental position. So how are we going to counteract this? We're going to account for drag. So obviously in our net force calculation, we have to first find the force of gravity, which is 0.5586 newtons in the negative direction. Now, the force of drag is negatively proportional to velocity, which means that the force of drag is equal to negative b, b being some arbitrary constant, times velocity that helps the graph better fit the actual phenomena that's occurring. And so here, as you go to our new revised GlowScript code, as you can see here, when you run the program, I've put arrows in here to show you that the forces of gravity and the forces of drag are equal in magnitude and opposite in direction. As you can see, the position versus time graph is curved at the beginning, but it gets less curved as you continue to go on closer towards the end. And that's because you are approaching a terminal velocity. Velocity versus time is now curved, and you can see it changing as you could also see it changing in the actual model. So to further show you proof that this is the better way of doing it, I've now put side by side the position without drag, and then the position of the model with drag. And as you can see, the position with drag, the model fits way, way better and much more accurately describes what's actually going on here. So the reason that this is because you eventually reach something that's called terminal velocity. Terminal velocity is achieved when the force of the drag pushing up on an object equals the force of gravity pulling it down. If the object were to reach terminal velocity, net force in the y direction would be equal to 0, meaning that the terminal velocity would be constant. In the model with drag included, you can clearly see that the velocity gets smaller and smaller in magnitude as time passes, eventually stabilizing. Finally, we were asked to ponder the question, what if the object was thrown instead of merely dropped? If the ball were to be thrown, the initial force would be greater in the negative y direction, but only as you are throwing the ball. As soon as you release the ball, as soon as it leaves your hand, the net force would be the same as our model with drag, because the drag coefficient would still be proportional to the velocity, and the force of gravity is unchanging. Therefore, it may take more time for the velocity to stabilize, but it would still reach the same terminal velocity, and F net would still eventually equal 0. That is all. Thank you guys so much.